something different, but something close. I'm going to talk again about defects, but different kinds of defects. More exactly, I will try to explain how defects coming from forging and shot peening operation can affect the fatigue strength. And this work has been carried out in the framework of a French project gathering several academic partners and several industrial partners. And the aim of this project was to study the influence of the surface integrity and the fatigue behavior of forged components. We used two car components, the connecting rod and the transmission shaft. And there were two main parts in this project: the process simulation, as you can see here for shot peening, and the characterization and modeling of the fatigue behavior. And about the fatigue, we investigate both the initiation phase and the propagation phase by X-ray tomography, but I will focus today only on the initiation part of the work. Okay, about the component under interest, it's that kind of component, a very well-known connecting rod made of pearlitic steel and obtained with several stages. We have stamping steps, shot blasting steps, and we observed something very interesting. What's specific about this work is that we used a huge number of connecting rods here to make statistics directly extracted from the production line. And for instance, if I take around 500 forged and shot blasting connecting rods directly from the production, and I try to make simple statistics about the kind of defects that can be observed, you see here that for 14% of the connecting rod, you can see that kind of defect. It's nothing else but some scale encrusted at the surface of the part, and some round defects for 15%, and the majority without defects. So we're going to have a look at what happens with those defects on the surface. And what we did, we used electric discharge machining to extract directly from the connecting rods some plain specimen. You see here the geometry of these specimens. And we apply plane bending purely reversed loading on this specimen. And we did that for different batches, different configurations, for as-forged surface before any mechanical surface treatment, for shot blasting treatment used to remove the scale from the surface, and for controlled, much more controlled shot peening, two types of shot peening, and we have a reference with no defect, no residual stresses, a polished batch. So we carried out many tests, and before every fatigue test, we perform a scan of the surface of all the specimens by using a profilometer, using an interferometry method. And you can see here the example of what we can observe for the as-forged case, for the shot, for two types of shot peenings with different shots, and for the shot blasting conditions. And you see here that some defects occurs in some location. And you see here the values of the roughness, the average roughness, and you can trust me, you can't use this roughness to get an estimation of the fatigue strength. And we also performed some measure of residual stress. And you see here the 4 conditions, and you observe some biaxial residual stress everywhere in depth. And we tried to get approximately the same maximum value of residual stress, around -500, but by changing the condition of the shot peening to get different depths of the profile. Well, now when we look at what happens after shot blasting, forging and then shot blasting, without any fatigue, what you see here is the effect of the ball. You know, here you recognize the impact of the ball, and under this impact, usually we can distinguish 4 layers from the surface. The first layer of extremely small grains, you can see this layer here. A second layer of heavily deformed grains, the transition layer, and the original material here. And you see here on this picture, again, the impact and the gradient of microstructure. What's very interesting here is that in some locations, due to the process, you can observe some cracks or fold, you know, as you can see here. You clearly see what I mean by fold on this picture. You don't know exactly what's this here, and when you use an EBSD map, you clearly see that this is scale. This is scale incrusted into the material and potentially leading to a crack. Now, if I look at the fracture surface of these components, you see here a shot blasted specimen, you see the surface of the specimen, and the fracture surface here. You see the impact, all the impacts of the different balls. And you see here that the crack initiates from an old macro defect in which, if we take a closer look, you see that at the bottom of this defect, you recognize here a fold. So to get a crack, you have 2 conditions. First, a macro defect, and second, a fold or a crack due to the action of the balls. Now, what is clear and what is great with this work is that for every fatigue test, we perform a scan at the surface. So we're able to find among all the defects which one is responsible for the crack. And you see here, if you look at this, at these 2 pictures, you see here that it's not easy to find which defects would be responsible for a crack initiation. And I can tell you that the crack initiates here and here. And now, if I try to draw for all our conditions a Kitagawa diagram with the fatigue strength in function of the square root of area, you've got that kind of points where you've got the reference here, the polished reference here. For the asphalt conditions, you see here the effect of the defect size. You observe a red scatter here. And for the shot blastings and the 2 conditions of shot peening, you see also the effect of the defect size. And what's important here is that even for the asphalt conditions, the presence of defects induce a drop of up to 34% compared to the reference, whereas for the other conditions, we got something like 35% increase of the fatigue strength. But what's important here is that you can see for the biggest defect in shot blasting, you got something which is close to the polished fatigue strength. So you have to take into account the effect of the defect and, of course, the effect of the residual stresses. It's what I'm going to do now in the fatigue strength modeling part. We did two things. First, simple things which consist in approximating each defect with a semi-ellipsoid. You see here this ellipsoid, and we try to build some statistics. And you see here, if I draw the square root of area for each specimen, you see here for instance, for specimen number 1, the blue point represents all the defects. We got something like 100 defects. And the red one is the defects leading to the crack. And the same for, if I use the Peterson law, the KF. And you see that the results is not that bad. We're able to find a good tendency, but we still don't get every details of what happens by this simple approximation of the defect. What's interesting here with this simple formulation is that when I take this case where you've got a big defect here and a smaller one, the crack initiates in this one where the stress concentration factor is the highest and not necessarily the square root of area. Now, we try to go further by using our surface scan and to create a model which is represent the real surface with the defect under interest and around 1 millimeter around the defect. We mesh this volume with at the surface a mesh size of 3.5 micrometers and at the bottom 100 micrometers, and we perform some finite element simulation. And what we observe is that kind for the same area talked to previously, we observe that kind of distribution of the stress, the sigma XX stress. And we are able, of course, to get some information about the stress concentration factor. But what we did next is to use something close to critical distance, but it's a non-local approach using the non-ground vacuum. And what we did is to try to introduce in the cranium the effect of the residual stresses. And if we perform such simulations and such assessment of the fatigue strength, we are able to clearly decrease a lot the scatter. You see here with this method the predicted fatigue strength in function of the experimental one, and you got here on the error bounds of plus or minus 15%, which is not bad when you look at the variety, the range of the defect size and the defect geometry. So to conclude, I just want to sum up my talk by saying that we studied several configurations of surface integrity, including the effect of microstructure gradient, residual stresses, surface topography, and deep presence of defects. We performed some plane bending tests, and by using a finite element simulation, we were able, a simple non-local multi-action fatigue criterion, we were able to predict the fatigue strength by taking into account the effect of the residual stresses with an error bound of plus or minus 15%. We did many other works in this project, like what? Like some studies about the crack growth at the synchrotron, and using, once again, some specimen showing extracting, machine from the connecting rod. And what you see on this picture is the crack growing from a defect we introduced at the specimen surface. The same here for the shot blasted. what you see is the development of the crack front in function of the number of cycles. And by doing so, we are able to investigate the effect of the crack growth rate in function of the stress intensity factor. And what is very surprising is that we don't observe any effect of the residual stresses on the crack growth. I think I'm done.
Okay, thank you very much.